but we'll get there. Okay, anybody have any other questions you want me to go over on our worksheet from Wednesday? Probably most of those problems are just a matter of going through your notes and trying to find the reactions. Some of the stuff that I think might be a little tricky is going to be some of the stereochemistry. Remember, the Lindlar catalyst is alkyne to a cis alkene. That's a very important reaction. A very, very useful reaction, by the way, that we'll see. We'll come back to that when we get into the alkynes, with synthesis without using alkynes. Okay. Feel pretty good about it? I don't see any hands. Nothing? Yes?
Can you go over D?
D.
The first D.
So D. Yeah. So D is a 7-member ring. Okay. Seven-member ring. Let's see that. Now we're hitting this with ozone under oxidative or reductive conditions. Oxidative. So what do aldehydes become under oxidative conditions? Carboxylic acids. Okay. So when I see ozone, what immediately do I think of when I see ozone? Pair of scissors. Okay. So a pair of scissors, and if it helps, just cut it right through there, and you're going to add an oxygen there and an oxygen there. Okay? But since you have hydrogens out here, under oxidative conditions, those also are going to be oxidized. Okay? So what this is going to give you is 1, 2, 3, 4, 5, 6, 7, is a 7-membered di carboxylic acid. 1, 2, 3, 4, 5, 6, 7. Okay, and it's going to put 1, 2, 1, 2, your geminal methyls. Okay. So if it helps under ozonolysis, you can rewrite this kind of in a goofy way for now. That's fine. I don't mind that. So you'll want to take this and say, let's say I break it through there. And so you could redraw that in this kind of, like I said, kind of goofy. Right? That's really what you have. That's the ozonolysis step. Because it's oxidative, then you're going to oxidize that carbon one step further. Okay? And so then the way I do these is just to count your carbons. 1, 2, 3, 4, 5, 6, 7. So just draw it in a line. 1, 2, 3, 4, 5, 6, 7. So you know your termini are here. And then just figure out, oh, well, those happen to be in the middle. So it doesn't matter if you go 2 from either direction. You put your geminals there. Okay? Cool? Any others?
Yeah, D on the bottom.
Which one? D on the bottom?
Yeah.
Okay, so this one. Okay, let's go over here. So this one is a fill in the reagents. So we started with an alkene. Okay, we started with an alkene, and we're going to go to question mark. How do we go to? Okay, so how did we get there? Well, what happened? Again, in retrosynthesis, when I'm looking at this, I know that I have 1, 2, 3, 4, 5, 6, 7 carbons. I have 1, 2, 3, 4, 5, 6, 7 carbons. Okay? So somehow, again, this molecule used to be attached. Oh, that's kind of cool. I do know a reaction that would detach right there, and that would give me the hydrogens if I had certain conditions. Okay? I know that this ultimately was attached there. So the reaction is not oxidative ozonolysis, it's reductive ozonolysis. So this would be O3 with HCl zinc. And that maintains the hydrogens as aldehydes. Okay? Okay? If the question would have asked you this, if they were carboxylic acids, then yeah, then it would have been oxidative workup, not reductive workup. Okay? But this one was reductive workup. Okay? Any other ones? And I'll try to do a summary sheet like this at the end of each chapter, so you can kind of work through what we've been talking about, work the kinks out before you see the exam.
We need D.
D. Yep. D on top?
On the bottom.
Bottom. Okay, so D on the bottom. Cool, I like that one. All right, so D on the bottom. Excuse me. All right. Man, I'm tired of this congestion. Okay, so I really only in my toolbox so far have, well, I have two ways to make a vicinal diol. All right. Looking at the stereochemistry of this, I'm in pretty good shape because I know that both hydroxyl groups are coming out at me, meaning whatever reagent I had came in from the top of this thing. All right? And I know that when it came in from the top of this thing, it put both alcohols on at the same time. Okay? So more than likely, this is going to be the osmium tetroxide with the base workup. And I believe our book has it with this in I think it does in T-butyl alcohol. That's the solvent. Okay? And that specifically comes in what we would call the cis plane. Cis plane would be above or below, and it'll be, let's see, what's our stereochemistry on this? Oh no, it's not. It's going to be an enantiomer mixture of that. So it's going to come in from the top and from the bottom. Okay, putting the hydroxyl groups on the same face. Now, what would have happened? Let's see if we could figure this out. What if I would have not given you this one? Does anybody have any idea how we could have made this one? Now, I didn't give this to you, but I want to know if anybody has an idea how we could have done that. Can't do it with osmium tetroxide, by the way. Just out of curiosity, just kind of an interesting, because that one is very specific to the chapter. All right. You had a chapter on oxyranes.
Bromine?
Okay, not bromine. Let me show you. Let me show you how if you hit this with MCPBA, what's that going to do? What is it? I heard it, epoxide. So that's going to make an epoxide. Now notice epoxides go on the same face. Right? They go on the same face, just like the osmium tetroxide. They want on the same face of this alkene. But what happens when I hit an epoxide with a base? Or in this case, I think you probably, I don't know if you even learned this. Let's do it under acid conditions. Either way, let's do it under acid conditions. Remember what happens when you hit an epoxide with an acid?
Wouldn't break it and then turn it.
Yeah. Yeah, in this case, it's kind of cool. It's going to protonate out here. So these are going to grab here. So you're going to protonate this. Okay. Then the water is going to be, because it's amphoteric, it's going to behave as a base, and it's going to come in and open that up. But notice how it does it. It does it from the opposite face. So it brings the hydroxyl group in from the opposite face as the leaving group, just like your typical SN2 reactions that you worked with all semester long, or I guess half the semester. So in this, you're going to have this product. You're going to have this. And then another water just comes in and reforms it. So it's an acid catalyzed opening. Grabs that, makes that, go into product. Yeah. Kind of cool. Yes?
How does that carbon group move over here?
Rotates.
It rotates?
Yeah, they just.
Oh, okay.
Yeah, once.
I
Yeah.
was looking at it and I was like,
It's a. I don't know why they drew it that way. It's probably just to confuse you.
Yeah.
It's because remember you have free rotation around this thing.
Yeah.
Now here's what I would ask. Let's take this one step further. Okay. Let's take this one step further. Let's say we don't know. How to do this? Yeah. Let's say we don't know that, and let's say that we don't have that methyl group there. Can you come up with a way? So this is going to be, so if we do our canonical parallel rules, this is going to be an R. Okay. This is going to be an R. Okay. So this one gave a set, not osmium. So MCPBA, metachloroperbenzoic acid, followed by acid, gives you an enantiomeric mixture of R and S. So you're going to get both of these out. Okay. If I hit that with osmium tetroxide and base, you're going to get this out. And if you look at this, you are, oh, did I do that one? No, fine. 1, 1, 2, that's R. In this case, though, it's S. Okay? So this one now has a plane of symmetry running through the molecule, so this is going to be a meso compound. Right? So the meso compound comes from osmium tetroxide and base. The racemic mixture comes from the opening up of the epoxide. That kind of cool? And then you could even complicate it further, say, was my starting compound for both of these, was it cis or trans? Yeah, kind of cool, right? There's a lot that goes on with the stereochemistry of especially these two reactions. Great question. Great. Again, adding to some of the stuff you probably saw last semester with Dr. Nagalis, opening up epoxides, forming cyclic ethers, oxirines. Okay, let's jump on into chapter 12. And this is a chapter in free radicals. Okay, so I'm not going to cover everything in this chapter. There's a couple things in here that are a little bit more for the advanced level. Again, I talk about photochemistry and radical chemistry more in advanced organic. It's because again, it's not typically something that is really beneficial or useful other than what we're going to go over. There are a couple things that are very important in here, so we'll talk about those today, and we'll put this to use. Yes?
Just a quick question. Is the answer key on Canvas on this one?
There's no answer key.
There's no answer key for it? Okay.
That's why I'll just give you, if there's ones you have questions on, ask me or,
Okay.
yeah. Okay, so chapter 12 is on free radicals. So the very first thing that I always like to do in talking about free radicals is to realize throughout your chemistry career, you've seen several arrows, but you've never seen a table explaining arrows. Isn't that kind of interesting?
Yeah.
You've used them, but you've probably never really seen them. We have a lot of different types of arrows in chemistry. Okay, the very first one you were introduced to was this one. This is your very first arrow, right? So if I take sodium hydroxide plus hydrochloric acid, it goes only to sodium chloride plus water, and it's exothermic, so it has some Gibbs energy, free energy, delta G, you can calculate it, blah, blah, blah. This means this reaction goes to completion. It only goes that way, okay? That's very important. The next one you saw in second semester, or actually you saw a second one in first semester of general chemistry, and that was this one. Okay, you remember what that arrow was for? What is it?
Equilibrium.
Nope, that's not equilibrium. Good guess.
Oh, yeah, that's right.
Reversible.
It is what?
It's not a reversible reaction.
Not reversible.
Resonance.
Resonance. Okay? So, resonance. So the carbonate doesn't look like this, because these electrons go, those electrons go, and it goes like this. So you saw this double-headed, or this double-headed arrow in Gen Chem. Probably never described it as the resonance arrow, but that's exactly what it is. And there's another one you can keep going. So that's the resonance arrow. Then, second semester general chemistry, you saw this one, sometimes abbreviated. This one, I don't like this form of it. It represents something different. I don't like this one. I do like that one. And what does that one mean?
That's the equilibrium.
This is your equilibrium. So you did your initial, your change, your equilibrium, your ice tables. You worked with that you work with La Chatillon's principle, right? You had the two sinks connected with the drain underneath, and so you added water and it shifted, and you took water out and it shifted, and you did all those beautiful equilibrium reactions. Now, just for the record, most reactions that you dealt with last semester with Dr. Nogales are equilibrium reactions. Okay? Most of these organic reactions go back and forth. We're just trying to get it to go to completion. Okay? Which is why we have the whole study of kinetics. Sometimes it just takes time to get the reaction to go. That's why you have to sit there at the bench and wait and stir the thing at temperature for an hour, because it does take time for all the little molecules to react. Okay? You were introduced to a new arrow last semester, and it was this one here. What was that one? It might have looked like this. It might have looked like this. But what is that?
Electron transfer?
Yeah, it's electron movement. It's a mechanism, right? So this is your mechanism arrow. But it's a specific mechanism arrow. This is why I'm going through this with you. This is a pair. This is a mechanism for a pair of electrons. So this mechanism means there's an electron here and there's an electron here. It's a pair of electrons that go. If you look at what I just did over here when we broke up our epoxide, the epoxide looked like this. And when I had the acid in the epoxide, I took a pair of electrons and I attacked hydrogen, meaning that pair of electrons is now making a bond with that hydrogen. Okay? So this is your mechanism arrow. This is a mechanism arrow for 2 electrons, and that's important. This is heterolytic, heterolytic bond movement or electron movement. This chapter gets into homolytic. Okay? Homolytic has a new arrow. So you're going to be, and by the way, there are other arrows. Let me just, if you want to complete this. This is typically a retrosynthesis arrow, meaning you have what's on the right, tell me what's on the left. You'll see that sometimes. You'll also see this arrow sometimes in research. This means it's future work. So again, there's a lot of different types of symbols and arrows, but in this chapter, we're introduced into a new arrow, and again, it's never mentioned in the chapter, at least to my knowledge. I don't read the textbooks typically, but you should. It's this arrow. Oh, that's a goofy looking thing. So what do you think that means?
1 electron.
1 electron, okay? So this is a homolytic electron movement. Okay? So, in free radical chemistry, we're only dealing with 1 electron. So you see a one-headed or a one-side-headed, and again stands for 1 electron. Okay, so you see a half an arrow or a half-headed arrow, whatever you want to call that. Okay, so our very first reaction in the photochemistry section, or I should say the free radical section, is one of the reactions that's really powerful, and that is working with chlorine gas and photons. Okay? Chlorine gas and photons. When you take chlorine gas and you irradiate it, that's typically abbreviated with H nu, that means photons. Those photons, if they're at the right frequency, they come down here and they excite those electrons to the point where the bond breaks. And when the bond breaks, 1 electron goes there and 1 electron goes there. Notice the single, or the side, the lopsided arrow. This is called chain initiation, step 1. Chain initiation. Are there 2 N's in initiation? No. Initiation, is that it?
It looks correct.
Does that look all right? Is that good? Okay. I hate spelling.
Me too.
I can never remember if it's 2 of those or 1 of those, or even like today I was doing potassium in general chemistry. I'm like, does potassium have 2 S's?
That's a good question.
It does? It does. See, that's the kind of stuff that just kills me. But like aluminum, does aluminum have 2 L's? No, it doesn't.
No.
So, you know, it's stuff like that. I'm just like, man, why can't it just be all organic chemistry? Okay, so step 1 is what we call chain initiation step. All right? So we're generating free radicals, really high energy free radicals. All right? Really high energy free radicals. We've excited this. We've added photons, we've added energy. Here is the crazy cool thing about photochemistry. Photochemistry, and those of you, like the couple of you that'll take advanced organic in here, photochemistry, we're able to do really crazy cool reactions at reasonable energy levels. Some molecules, you can't heat up past 150 and the thing decomposes. So you can't do real aggressive chemistry, you just destroy the molecule. Photochemistry allows us to do things at a much lower temperature because we're adding energy internally by the vibration of the photons. So we're not heating the molecule, we're adding energy non-thermally, but we're adding energy. The frustrating thing about photochemistry is oftentimes it's not predictable. So you might try it thinking you're going to get something and you get a mess. All right? So photochemistry or free radical chemistry is often very difficult chemistry to do. Industrially, they'll do it. I'll explain that, what I mean by that, because they have ways to get around this. Has anybody had a filling where they took the blue light and they shined it in your mouth? Does anyone remember that? Okay, that's a polymer. That's a photo-organic polymer that is actually forming bonds by adding photons, blue light. All right, it's kind of a cool new technology. Most of the stuff in my mouth is all mercury lead acetate. And it's probably seeping into my liver as I speak. So it's nice that you guys are working with organic polymers, not amalgamas of mercury and silver. Okay, so this is the initiation step. This is the step that gets the process rolling. Once you have these high energy radicals, you can put those into the presence of something and I'll do an R group here. You could put those in the presence of another molecule that has a certain bond energy associated with it. All right, and if you go back to general chemistry, we calculated all these bond dissociation things, right? We used Hess's law to come all the way around because we didn't know the direct, so we did it each step individually. We worked with that, but again, this bond right here has an energy associated with it, but it's low enough that the energy of this can excite that, okay? So this is called step 2, or chain propagation step. Okay, initiation, propagation. That's spelled wrong, spelled correct. Okay, and in this phase, what happens, and you can see why it's called propagation. Okay, I broke up the carbon-hydrogen bond with those electrons. All right, and the reason again it's called propagation is because what did I get out? Well, I got out another free radical. I got a different free radical, but nonetheless I got a free radical. And this is where the propagation step, it can go on and on and on and on and on and on. It just keeps on going. All right, this radical, if you're in a reaction, this radical can then grab a chlorine, it can grab a radical, it can even come over and grab another radical. It just goes on and on and on and keeps forming radicals. Okay? Step 3 is chain. So it's initiation, propagation, termination. Chain termination. Chain termination happens when the free radical finds another free radical. Notice if this free radical found a chlorine, so if this found a chlorine, what type of step would that be? Would that be termination, or would that be propagation?
Propagation.
That would be propagation, because it generates another chlorine, right? Another chlorine radical. So that would be propagation. But if the radical finds another radical, then we go to termination, and that's ultimately when we end up with one of the products that's possible. Okay? Okay? That makes sense? And this thing could find a chlorine, it could also find another one of itself, which is kind of weird. This thing could find another one of these floating around, because again, it's a high energy. Once you initiate it, right? This thing could do this, and notice what we get out. This is also a termination, but it terminates it by making a carbon-carbon bond. Okay, so you can see, you can get a lot of different reactions out of this thing. All right? So the key point of this is initiating with a photon, propagating where the reaction continues to generate radicals or free electrons, and then finally termination when it actually reform the covalent bond. Okay? So in industry, and again, photochemistry isn't super practical in the working synthesis lab. It's very rare to be set up to do photochemistry. My postdoc at Berkeley was photoorganic chemistry, so I kind of enjoy it. I kind of think it's neat. It's frustrating because you don't always get what you think. Sometimes you get something you can't explain. And so I always kind of found it fascinating. It was one of the things when I was in graduate school, a lot of the mechanisms make sense. SN1, SN2, E1, E2, all that kind of just sticks and it works for the way my brain thinks. Photochemistry never sat well with me. And so I think that's one of the reasons why I was drawn to doing a postdoc in photoorganic chemistry, because it was just a fascinating topic. And it turns out that it's actually much more difficult in the practical working lab than I expected, but it still was a very fascinating time of my life, of my study. But what happens with this reaction, if I take something like methane gas and I hit it with chlorine gas and light, I get out get out chloromethane. I get out dichloromethane. I get out chloroform, or trichloromethane, and I get out carbon tetrachloride, or tetrachloromethane, okay? So you're thinking to yourself, well, that's not very synthetically useful, is it? Well, turns out it's not at this level, but here's the cool thing. We have used methylene chloride in lab, DCM, dichloromethane, right? We use it a lot, it's a great solvent. I use it all the time. We used to use chloroform. When I was in grad school, chloroform was kind of the solvent of choice. Chloroform has been shown now to be a little bit carcinogenic, so we're moving back to DCM, which is still pretty safe. Chloroform is actually a better solvent. It dissolves more things. It's a little bit more polar, but anyway, that's neither here nor there. Methylchlorine is a gas, so it doesn't really, you can't really work with that. Carbon tet's also somewhat carcinogenic. We use that for NMR, some types of NMR experiments. But in a working lab, this is pretty useless to us. But here's the cool thing. Industrial, this is really practical, because in an industry, they can have a great big giant fractional distillation column, and it's like 7 or 8 stories tall, that big, like massive, like when you see those cracking plants down in Houston and out of Seattle, those big petroleum distillation places, they can actually pull out, carbon tet comes off down here, chloroform comes off here, so they fractionate, DCM comes off here, and then methyl chloromethane comes off here. So they can actually separate out. So when we're using DCM, this is the type of reaction that we've done. It's practical for them, not really practical when we're in a working organic lab. So we have to come up with ways that are practical for us to do this chemistry. What are those? Well, great question. Let's look at 2 different types of free radical reactions. If I take propane and I chlorinate propane, okay. If I take propane and I hit it with chlorine and light, I get 2 main products. All right, I get a chlorine here, and I get a chlorine out on the end. Okay. Now, the interesting thing about this when I do this is I get 45%. I get 45% 2-chloropropane, and I get out 55% of the 1-chloropropane. Okay, so you might be thinking to yourself, oh, I get more of the chlorine going on the primary carbon than the secondary carbon. Okay? So if you look at propane, propane has 2 primary carbons and a secondary carbon. So this ratio isn't a fair ratio, is it? How many primary protons do I have? How many? Primary.
6.
Okay? So I have to divide this number to actually understand, oh, not that one, sorry. I have to actually divide that by 6 to see what the ratio really is of primary to secondary protons. How many secondary protons do I have? 2, 1, 2. So I need to divide this by 2. So when I do this, about the only math we're going to do in this class,
That's sad.
right? I know, right? All that math you took and you don't get to use it. Divided by 6. So this equals 9.17. This ratio equals 22.5. Okay? So in order to find out the ratio of primary to secondary, I need to divide both of these by 9.17. Obviously that, I can do that math. That equals 1. 22.5 divided by 9.17 equals 2.5. Okay? Worked out right? 45. Okay? So we roughly have about a 1 to 2.5 ratio of working with secondary over primary. So it is true that secondary are more reactive than primary. All right? See how this is working? So when I do a chlorination step, what happens with this reaction is I have roughly a 1 to 2.5 and roughly about a 1 to 4, 1 to, if we do some further math, and we can do it, I'm not going to take you through it today, we don't need to. But you roughly have about a 1 to 5 ratio, 1 to 4, a little around 5 ratio of a tertiary. So here's the problem with the reaction. When I do a chlorination, using photochemistry, okay, okay, so if you notice, I'm looking at that, that's not the right ratio. So I've got this backwards. So this, did I just do that wrong? No, that's right, that's right. So this is 55, this is 40, that's right. I'm looking at it going, that's not the right ratio, it should be 1.37. 1 to 3.7. Okay, so let's do that again. So just fix that in your notes. So let's go 55, I know, right? Cross it out. Cross it out. Okay, 45, that's so much better. Okay, 45, 7. Okay, now divide both by 7.5. And 7.5, we actually get the correct ratio, which should be 3.7. Boom, look at that. Okay, so, because I know it's 1 to 3.7, I'm looking at it going at 1.4, 1.5, that's right. I think it's 1. Okay, so here's the practical side of this reaction. When I do a chlorination, primary to secondary to tertiary is 1 to 3.7 to roughly 5, okay? Meaning, synthetically, that's not super useful. Because the last thing I want to have to try to figure out is how do I separate out multiple chlorinated products. But here's the cool thing. The chlorine is really aggressive. It doesn't really care about protons. It just comes in and it just steals them. If I do bromination and go through the same exercise of primary, secondary, tertiary, primary is 1, secondary is 100, tertiary is 2,000. Now we're talking. And this is why in photochemistry, in organic chemistry, we do use bromination as a synthetic tool. Okay? So for example, if I were to brominate, if I did this reaction here, if I took propane and I brominated it instead of chlorinated it, chlorinating it, we already saw what happens. I get 2 products out. All right? But when I brominate this, I get out 2 products, but look at the ratio. I get out bromine 98%, or 98, I shouldn't do percentages, that's not the actual yield, it's the ratio. 98 plus bromine to 2, okay? Now that's already become synthetically useful. I'll take a 98:2 ratio on a reaction. But here's the real crazy cool thing about bromine. Because this is 2,000 to 1 or 100, if I take and brominate a tertiary, if I brominate a tertiary alkane, I get only that. Okay? Now why is that cool? Well, that's cool and useful because of this. One of the things that we're going to build as the semester progresses is trying to find handles for the molecules on which the functional group transformations can take place. So watch now what I can do. I can take something like methylcyclohexane. By the way, if I chlorinated my methylcyclohexane, watch what happens. So if I chlorinate my methylcyclohexane, I get out this. I get out this. I get out this. I get out this. And I get out this. And not only that, I also get a bunch of dichlorines and a bunch of trichlorines. And you see that synthetically it's just not useful. But in bromination, I can come in and I can hit this with bromine and light, and I get only this out. Okay? Now watch what happens. When I put that bromine on right there, I now have a handle on an otherwise pretty useless molecule. Okay? So something like methylcyclohexane, you might use it for, probably is, I mean, it's actually very flammable, but probably is like a solvent that you could use, burn it, you could get carbon dioxide and water out. But now all of a sudden, I went from something with no handle, all these carbons are sp2 carbons, there's no handle on them, to a carbon with a handle. So what I can do with this now is I can come in and do all those reactions that I know. I can hit it with T-butoxide, a strong hindered base, in T-butyl alcohol with some heat. And I now know that I'm going to favor elimination, not substitution, because I'm not a strong nucleophile. I'm a weak nucleophile, strong base, meaning I'm going to grab a proton here and here. Would I get 2 products out? Yeah, I'd get a minor product out, and this goes back to Zaitsev's rule. But this is going to be the major, and you'll get I'll put it down here. You'll get a little, but you're not going to get very much of that. You'll get less than 5%. So you don't have to worry about that. I went from, again, a very non-reactive alkane to an alkyl halide that's a good leaving group to an alkene. Oh dear, now we have a lot we can do with that. We could hit this with MCPBA, and we could form epoxide. Okay. We could hit this with, what else? We could hit this with ozone under reducing conditions. And we could form this. Isn't that kind of cool? Et cetera, et cetera. There's a lot of other different reactions you could go do from an alkene. We could hit it with the osmium tetroxide. Some base. Form the genital diol, or excuse me, distal diol. Isn't that cool? So what we're doing is we're going from something that is synthetically kind of useless or dead with one reaction that specifically puts a bromine on a tertiary carbon. And now I've got a handle on the molecule, and I can take something that's synthetically not very interesting and begin to build something very interesting. Okay? And so this is how we're going to build through the semester. You saw these three reactions last chapter. We just added a new reaction that's synthetically useful in free radical chemistry. Okay? This is from last semester with Dr. Nagales when you learned about the elimination with a strong base, poor nucleophile. It's a poor nucleophile because the T-butyl group comes in and it can't get into the carbon. All right, so we use T-butyl there. So we push this instead of substitution, we push it to elimination, which is what we want. Once we're at the alkene, we take the major Zaitsev product of the alkene and we begin to synthetically build on it with the reactions that we just learned. Yes?
So in the second one that you did, what if you did it under
Yeah, great. Yeah, and you could do that too. If we did it under oxidation conditions, you're going to put an oxygen right there. Yeah, good. Excellent. See, the chemistry that we just learned is in our toolbox. We're learning new chemistry, old chemistry, and we're applying all of that across 12 chapters. Isn't that kind of fun? And this will build. By the end of the semester, your toolbox will be so large, because right now you don't really know a whole lot about this reaction. You don't know the reaction between aldehydes, and ketones, right? They form aldols, and we're going to learn all that. So we're going to be able to open this up, and we're going to have those electrons attack that carbonyl. You're going to see how that works. It's beautiful. It's super cool stuff. Okay, that all builds on these reactions, which is why we need to learn them, put those in the working toolbox so that we can see a synthetic scheme like this. Because I'm going to ask you on an exam 1, I'm going to say the most difficult question that you're going to have is, starting with, this is what it will look like. And it'll be verbal. Starting with methyl cyclohexane, synthesize, and I'll draw this molecule. You have to show me how to synthesize it. Okay, so we're going to learn how to retrosynthesis, go backwards. How does this break up? How can I put this back together to form this? How does that go to there, and how does that come from there, okay? And that's what we'll be building on as we learn these tools of synthesis. Okay, our last reaction for the day before we head off for a nice weekend, a nice weekend break, is ambromosuccinimide. Ambromosuccinimide is a reaction that is specifically targets two different types of protons. This used to be taught with the alkene chapter, but Sorrell breaks it up to the free radical chapter, which is fine. Again, I'm going to go back and review. Okay, this is toluene. We haven't been there yet. We're not there yet. Toluene is a really nice solvent. I have it in my shop. It's great for removing paints. It actually melts certain plastics. It's kind of a cool, used to be used in this, when kids actually did models instead of Fortnite. This was actually the active ingredient in the model glue that actually melted the plastic together to form the little pieces of the airplane or whatever it was. It smells really good. I love the smell of that stuff. Make you hire a kite, but it's good smelling. These are called benzylic protons. Okay, this is called the benzylic carbon. Okay, it's special. It's a very special carbon. Those are very special hydrogens. All right. Last semester, you learned about this group. All right. These are allylic hydrogens. I think it has two L's. Hydrogens. This is an allylic carbon. Okay. They are very special locations, and the reason why they're special locations is because they are adjacent to an sp2 carbon. Right? So if you remember, this is an sp2 carbon. This is an sp2 carbon. Right? So because that's next to an sp2 carbon, if I remove this entire thing and form a carbocation here, you might know it as a carbocation, notice what happens. Under conditions of a base, when the base takes that hydrogen off, now let's do acid. Let's do an acid. I'm gonna do this number. So when we have an acid that takes this base, or takes that off, notice what it leaves in its wake. It leaves a carbocation. All right, and when you did your whole study of carbocation stability, you learned that tertiary is more stable than secondary, which is more stable than primary. But in the alkene chapter, you probably learned about the allylic carbocation, and it's super stable. And the reason it's stable is because the solution to pollution is dilution. So when I have a high energy compound, I can resonate it with my resonance arrow, and I can delocalize that charge across two centers. So I can delocalize the carbocation across two centers. That's what makes them so stable, and what makes them so special. So that's why the allylic carbon and the allylic proton are special, because they're adjacent to the sp2 carbon. Likewise, the benzylic carbon and benzylic hydrogens are adjacent to an sp2 carbon in the aromatic ring. So, if I react this compound with N-bromosuccinimide. N-bromosuccinimide looks like this. Okay, we just call it NBS. It goes through a free radical mechanism whereby it initiates basically forming a bromine radical here, okay, which puts the bromine on here. So the NBS reaction is a nice reaction for two reasons. One, I can put a handle on a molecule in a controlled area as long as it's allylic. But two, it maintains the alkene. It doesn't kill the alkene. If I hit this with HBr, if you go back to last semester, you notice that it forms this plus a little bit of this. All right? Those are different. HBr is an addition reaction to an alkene. Markovnikov's rule says this is the major, this is the minor. But MBS maintains the alkene, doesn't kill it, because it's pulling off the proton out here free radically. That's why we put this in the free radical chapter. All right? Likewise, benzylic hydrogens under NBS also take off benzylic protons and do not affect aromaticity. So it puts a handle on a molecule that already has a handle. So this molecule has two handles on it. Okay? That's pretty synthetically useful. And we'll build on that towards the end of this chapter. Now, I have like 30 seconds left. The limitation of the MBS reaction is this. It doesn't care where the alkene is. It will put a bromine on wherever there's an alkene. So if you have a symmetrical alkene, you're golden. If you have a non-symmetrical alkene, you're going to get multiple products out. So if I hit this molecule with NBS, I'm going to get out one product. All right, I'll actually get out an enantiomeric mixture, but I'm not going to, because that's a racemic. You get a racemic mixture. But if I reacted this molecule with NBS, you're going to get out a mixture. And unfortunately, it's going to be close to 50-50. Because NBS is a free radical that doesn't really care. You're going to get out that, plus you're going to get out this. And it's going to be roughly, not exactly, but it'll be roughly 50-50, okay? So that is the limitation to the NBS reaction. If you have an unsymmetrical starting compound, you can't specify which one it should go to. It's going to go to both. You're going to have a tiny bit more of this one. Might be like a 55-45 thing, but not much more. Okay, and that's one of the downsides of the MBS reaction. You do have to have a symmetrical molecule. When you're symmetrical, It's a very practical, very, very nice reaction. In fact, I think synthetically, look at this thing. Look what we do with this. Hit this one. Hit this with potassium t-butoxide and t-butyl alcohol. That's going to eliminate this. Oh, that's pretty slick. Check that out. Man. Oh, and then I'm going to react that with something like an aldehyde. And oh my word, check this out. I'm going to make, look at that. Isn't that cool? I just did a Diels-Alder. Huh, that's pretty
Oh,
trick.
I love Diels-Alder.
It's pretty trick, right? So you can see how we're going to use these reactions and we're going to build on them in context, again, of learning new reactions. So I take an alkene, make a diene, add it to a Diels-Alder, and I get out, that's so cool, I get out a nice Diels-Alder reaction. Isn't that fun?
Yes.
Okay, we will build. This is a semester of building, and we'll pick up on Monday. Probably get through most of the rest of the chapter because again, there's some things I'm just not going to hold you accountable for, and we'll get into some other pretty neat reactions. All right, have a great weekend. Enjoy it. Enjoy the rest.